Okay, here we go again. Welcome back. Today's topic is the stack of all curves. But before we get to that, I kind of want to, you know, cover or remind you exactly where we are. So, like the overall goal of the course is to show this theorem up here, and right now we're getting closer and closer. And so we've introduced stable curves. And this has allowed us to define the stack mg bar, or at least the pre-stack. And we almost know that mg bar, whoops, my handwriting is getting worse. Mg bar is a dm stack, which is smooth over spec z of relative dimension 3g minus 3. In fact, the only missing ingredient other than connecting some dots is to show that mg bar is algebraic. And this is what one of the topics we're gonna cover today. And in fact, there's many ways to show algebricity. You know, that we had an argument to show that mg was algebraic using the Hilbert scheme, and we could just replicate that argument if we want to, but just to show you, in the goal of showing you another flavor of types of methods in moduli theory, I'm going to proceed by showing that the entire stack of curves is algebraic, and then that mg bar is an open substack and therefore also algebraic. And we also know that we almost know that there exists a coarse moduli space. And the missing ingredient here is just, in order to apply the Kiyomori theorem, we need to know mg bar is separated. And so we won't cover that today, but hopefully next time when we discuss stable reduction. Okay, that's where we are. But I think I'd like to take this opportunity to give a sort of a wider perspective on moduli problems and how one sort of approaches this question of constructing projective moduli spaces. And the way I see it is really like a 6-step process towards constructing projective moduli that I'd like to sort of summarize first. And you know, here in the setup, we're going to take x to be your moduli stack of interest. You know, and on the right-hand side, I'm going to spell out these steps in the case when x is mg bar. So for us, x is the stack mg bar of stable curves. But another example to keep in mind is maybe the moduli stack of semi-stable vector bundles over a fixed curve. Right, and in order to, and so maybe in this setup, what I would like to do is also consider not just x, but an enlargement. So I'm going to let M be a stack containing x, which is an enlargement. In our case, we're going to take M to be the moduli stack of all curves. And then we just like introduce the definition. We're going to call a field valued point of M stable if it's contained inside X, the substack X. All right, and the goal, okay, and so it's a 6-step process, and the first step is what I call algebricity. And here what this means is that the enlargement M is an algebraic stack of finite type, locally a finite type. Over whatever your base is. And yeah, this step is today's goal, is to show that the entire stack of all curves is algebraic. Right, so after you have that, then in order to argue that your stack of interest, X, is algebraic, you need to show openness of stability. What this means is, given maybe an object E of the larger stack of the enlargement M over some base T, you want to consider the set of all points T in T such that when I take E and I restrict it to the residue field of T, it's stable. And I want this locus in T to be open. That's what I mean by openness of stability. And what that implies is that this substack X of M is an open substack. So once you show that M is algebraic, you also get that X is algebraic. And locally a finite type. But in the end, we want to construct the projective varieties. Projective varieties are quasi-compact and of like finite type. So step 3 is boundedness of stability. Here you need to show that X is of finite type, or equivalently, that it's quasi-compact. Or in other words, that there's a bounded family, a finite type family, a finite type like a variety, and a family of objects over that, such that every object of interest in your stack X appears as a fiber of this given family. Right. Oh, and for us, openness of stability. Okay, I didn't explain how we're going to know step 2. We've essentially shown step 2. It's going to follow from the 2 openness statements we've already shown. We've shown openness of the nodal locus in an arbitrary family of curves, and then we've also shown the openness of stability for a family of nodal curves. And then for step 3, what we're going to use here is it's going to follow from the fact that if I have a stable family, then the third power of the relative canonical is very ample. This allows us to get quasi-compactness because we can rely on the quasi-compactness of a Hilbert scheme. Right, in step 4, we've already discussed the existence of the coarse moduli space, and the way in this step you want to apply the Kiel-Mori theorem to show that there exists a coarse moduli space. And here you need to know that X is separated. And then stable reduction is just the statement that X satisfies the valuative criterion for properness, or that X is proper, which then implies that this algebraic space X, the coarse moduli space, is also proper. And so these two steps we're going to do probably next time when we cover stable reduction. We'll show that MG, at least in characteristic 0, is proper. And the final step, perhaps the most difficult, is projectivity, which is that the coarse moduli space is actually projective. And this will be our final lecture, where I'll give my best attempt at giving a recap of a vague overview of Kolar's argument. Right, so that's sort of a summary of where we're headed, and at the same time, I wanted to put this sort of in a framework to construct projective moduli problems, not just for MG bar, but for other moduli. And so, for instance, like since we've already defined stable curves, we could just show directly that MG bar is algebraic, but certainly for like the stack of semi-stable vector bundles on a curve, I don't know how you're going to get algebricity without first showing that the stack of all bundles is algebraic and then showing semi-stability as an open condition. But yeah, I'm gonna pause here and take questions.
So why yeah, the stack of all curves is a stack.
Oh,
Yeah,
we'll
I
cover
mean
that.
okay.
Yeah, I'll return to that later when that'll be the first step in the proof. Other questions? Okay. And yeah, before getting to the stack of all curves, I just want to give a quick recap on stable curves, and we're going to need one additional property about stable curves, namely contracting the contraction morphism. So let me give a quick recap on stable curves, and I'll just walk you through this. We covered all of this last time, and so we're defining not just we're defining n-pointed curves. So this is just as a connected nodal projective. C is a connected nodal projective curve, and I'm taking n points here that are distinct and smooth. This is important that they're distinct and smooth. And then stability is the additional requirement of these conditions 1 and 2. One is that every rational subcurve, every P1, contains at least 3 special points, where a special point means node or marked. And then we rule out just a genus 1 curve without any points. And so in this picture below, these are stable, and you realize that each of these rational curves, this one contains 2 nodes and 1 mark point. And in these cases, this contains 1 node and 2 mark points. And then this one contains 3 nodes. So this is an example of stability. This curve here is not stable because you can't mark a node. And then there's this notion of a slightly weaker condition of semi-stability, where you allow curves that have a rational subcurve meeting at only 2 points. And then dropping 1 and 2 entirely, you just have this notion of a pre-stable curve. A pre-stable curve is just a nodal curve, where again, if you have mark points, they're distinct and smooth. Right, and we have this nice characterization of stability, that given this proposition below, if we have an n-pointed pre-stable curve, so we're already assuming the mark points are distinct and smooth, then we have 3 equivalent characterizations. It's either stable, or the automorphism group is finite, or if you take the dualizing sheaf and twist by the marked points, then it's ample. Great. And one of the major things that we cover at the end was we characterize the dimension of these X groups. So this we'll use this result later because this X group classifies automorphisms, deformations, and obstructions. And so we can conclude that mg bar is smooth, and we can compute its dimension. So that's what a stable curve is over a field. And moving forward, we need to define families. And so we define them as you have a family of n-pointed nodal curves. And here, if you have there's a family of n-pointed nodal curves is just a flat, proper, finitely presented morphism of schemes. And then you have n arbitrary sections. And you require that the geometric fibers are reduced nodal connected curves. And then by putting additional constraints on the family, you get families of n-pointed stable curves, semi-stable curves, and pre-stable curves. And here it's sort of the simplest case in all that you can have in moduli, where you're just requiring a condition on the fibers of this family. And sort of the 2 properties we showed about families of stable curves are written below. One is that that if you take the relative dualizing sheaf and you twist by the sections, then it's at least when you take the third tensor power, it's relatively very ample. And moreover, by like a cohomology and base change argument, you can get that it's pushed forward as a vector bundle, and you can compute its rank by Riemann Roch. And then finally, we did show open assistability. Essentially, we had two methods using either of these equivalent characterizations of stable curves, where if you have if you have a family of n-pointed nodal curves, then the stable locus is open. Okay, that's where we were. And the one additional ingredient I want to cover now is sort of contraction morphisms from pre-stable curves to stable curves. Okay, so first I'm going to introduce another definition, but it's sort of, it's quite natural. I'm going to introduce the notion of a rational tail or bridge. And so we're starting with an n-pointed pre-stable curve. And then we call a smooth rational subcurve, E in C, we call it either a rational tail or a rational bridge, where it's a rational tail if it intersects the rest of the curve at one point and contains no marked points. That's a tail. So in the picture below, that's case A. This is a rational tail. And these other two in B and C, these are examples of rational bridges, where in the definition, it meets the rest of the curve in 2 points, and or in just 1 point, but then the other point is a marked point. I mean, I guess, technically, I guess in the genus 2 case, or I guess you would also consider a genus 1 curve with just 2 marked points. Or sorry, a genus. Oh yeah, but that wouldn't. Yeah, you could count that too as a stable curve, as a rational bridge. Anyway, any questions on that definition? Rational tail and rational bridge. And we have sort of to connect this with the notion of stability. We have this like simple observation that if you take an n-pointed pre-stable curve, then it's stable if and only if there do not exist rational tails or bridges. And it's semi-stable if and only if there does not exist any rational tails. Right. And you can also have an example in the bottom here, you can also have like chains of rational tails. Like you could just keep connecting P1s, or you can also have chains of rational bridges. Right, so what we'd like to do is we'd like to contract the rational tails in bridges. And so let's consider if we have a pre-stable curve. Let's define sort of the contraction, or you could also call this the stable model or the stabilization. Let's just say it's the proper curve obtained by removing all rational tails and bridges. And let's say the EIs. And so in other words, I take C, I remove the union of all the rational tails and rational bridges, and then I just take the closure. And I have a morphism from C to this curve, which is pi. And I'm gonna just have these points Pi here. Let's just let Pi prime be the images. And then sort of just by construction, you see that what you obtain is stable. And so really you can go from a pre-stable curve to a stable curve just by removing the rational tails and bridges. And so I've kind of drawn some examples below where you just remove everything that's in red. And maybe in point C here, if I have a rational bridge with a marked point, then the image, I just follow the marked point along the contraction. And so I get a marked point where the node was before. Okay, so that seems relatively straightforward, but we want to do this in families. And here's where the challenge, one of the challenges comes in. We want to contract rational tails and bridges in families. This can be done, but requires a lot of work. So I'm basically just going to state the result. Yeah, so this is the result we want.
Sorry, can I ask something?
Yes.
So in example B, we are not just removing the tails. We are also, we are contracting the tails, right? We are not just removing them and taking the closure.
Yeah. Okay, good. Yeah, good point. Yeah, you're pointing out that, right, that my explanation was a little too simple. Right. Thank you. Yeah, if you did this construction where you just remove them and take the closure, you're not going to connect them at a node. You're right. Okay, but I think you also see how to correct it. Yeah.
Excuse me, the idea should be even in a case like part A, you are contracting them, right? You're not just, that's actually what you're doing, right?
Yes.
If we want to generalize to one procedure that covers all the situations, it's always contraction, right?
Yes. But I think the point was that, yeah, it's always, contraction. Yes.
It's never actually just removal.
Well, okay, okay, maybe it depends on how what you mean. It's maybe, it's best viewed as contracting them. I mean, in this case,
it can always be viewed that way. Yes, so contraction morphism.
Mm-hmm. Right. So maybe just saying here, this is not quite right. Okay, so what we want to do, we want an analogous procedure in families. So let me walk you through the statement. So I'm taking a family of pre-stable curves, and I would like a morphism from C to the stabilization or the stable model, where this is now a family of stable curves, and such that on fibers it's what we saw on the last page, so that it is just the map contracting rational tails and bridges. And then moreover, you have some nice additional properties that you can imagine are useful, that you understand the push forward of the structure sheaf, and you have vanishing of cohomology. And maybe, in the semi-stable case, you can even describe that the dualizing sheaf twisted is the pullback of the dualizing sheaf. And note that since this is now a stable family, this is a relatively ample line level. And maybe give you an example of what this procedure is. Let's suppose we have a family of smooth curves degenerating to a curve with a rational tail. Say a fibered over, say, a smooth curve. And let's call this curve, this tail E. And in this case, we'd like to contract this, but only in the central fiber. And note that here, let's suppose that this is all living over a point 0, and if you take the central fiber C0, this is just the sum of E plus the complement as a divisor. And so because if you intersect two, if you take a fiber in this family and you take its self-intersection, you're going to get 0. So in a similar way, if you take the whole fiber and intersect it just with E, because you can move the fiber, that you get a zero intersection. And this can be computed then as E squared plus the complement of E dot E. And so what you see is that if E is a rational tail, then it intersects the rest of the component at one point. And so you get E squared is -1. And on the other hand, if it's a rational bridge, you get self-intersection -2. In either cases, you can use, the birational geometry of surfaces and essentially Castelnuova's criteria to contract this exceptional divisor. And that's what we're after. And so I do want to tell you like at least two methods to establish this. Both are going to be vague sketches because I think that the first sketch is easier to fill in the details because the ideas are very similar to Castelnuova's contraction lemma. Was there a question? Yeah, okay, and in this case, let's assume that we start with a semi-stable family. And this, I think, is going to be enough for our applications. But so here, it's sort of clear what you want to do. You have your pre-stable family, or your semi-stable family, where you may have some rational bridges. And you note that the dualizing sheaf on a rational bridge is not going to be positive. It's going to be degree 0. But the dualizing sheaf on a stable family is ample. So the natural thing to do is you just take the family defined by the relative canonical line bundle. That is, you take if this map is pi, I take the push forward of powers of the relative canonical. I take the direct sum, and I take the proj, relative proj, and you need to show that this is finitely generated. And has the expected behavior. So there are some details here, but I'd rather skip them and just give maybe an outline of a second argument as well, which also works in a non-semi-stable case. And here, there's a lot of ingredients in this argument I'm about to give you. And I'm not going to do the argument justice, so I'm going to forward you to where you can read all about it in the Stacks project. But I'm also giving this argument, the second argument, because I think it's kind of a nice conceptual argument and also exposes you to other ideas in moduli theory. Namely, like we're going to follow this sort of local to global argument, where, okay, so there's several steps. The first step is, well, you use Noetherian approximation to reduce to the case where S is finite type over Z. And then yeah, you show uniqueness of the stable model. This also requires work. Okay, and then now getting to the local global part. So given a point S in the base, we have sort of a contraction. Let's call this. This is just a curve now over a field, and I could contract the rational tails and bridges as I did on the previous slide. But the point is we want to do this in families. So let's call this Y0. And so our picture here is that we have a family of curves, and that over at the residue field at the fiber, this, And let's call this S0, and let's call that, and let's just start taking the nilpotent thickenings. So I'm just introducing some notation here. C0, let's call this fiber C1. And we can also take the spectrum of the completion and the corresponding fiber product. So we have a Cartesian diagram like this. And what we have to start, let me give myself some more space. We already have a map from C0 to Y0. And what we'd like to do is extend this from the fiber to globally over to the town neighborhood of S. Okay, so the third step is just to use deformation theory. So I'm not giving any details here, but I'm just outlining sort of a general technique in moduli theory to go from the local to global. And we're actually going to use this argument again later today. So we're going to use deformation theory to extend what's happening over the fiber to what's happened to these nilpotent neighborhoods. So this now gives us maybe a map from C1 to Y1 to Y2 and so on. And then you need to go from these nilpotent thickenings to a formal neighborhood. So here you algebraize to a map from C hat to Y hat. And then you need to go from the complete local neighborhood to an Étale neighborhood, which is where you apply the powerful Artin approximation. What this gives you, it tells you that there's an Étale neighborhood, S prime to S, and a family and a morphism, say, to Y prime. So this gives us in our picture, maybe an S prime to an S. You take the fiber, and you have a map now to Y prime. And then in the final step, because we have uniqueness, and we have an extension over an Étale neighborhood, you can use the uniqueness to descend. Use uniqueness to descend to a map C to Y. So in the end, what we get, I'll do it in red, is a map from C to Y, which is the desired, and Y here is a family of now stable curves over S. A very vague outline. I should apologize. Sorry. Okay, any questions on this? All right, now I'm going to get to the main part of the lecture, to the stack of all curves. All right. And I'm gonna start by even redefining what we mean by a curve. Perhaps I should have defined this defined it as follows the first time. So I'll define a curve as a scheme of finite type over a field of dimension 1. So we're not assuming pure dimension 1 or connected. And the reason for this is something that's that's familiar to you, that if you take, you could take a rational normal curve in P3, say given by this embedding x cubed, x squared y, xy squared, and then y cubed. But I can consider this, I can introduce a parameter here, t, and this is a rational normal curve for all t non-zero. But if you take the limit, so if you take this limit as t goes to 0, what you see is, this example is even in Hartshorne, the flat limit, what you get is a plain nodal curve set theoretically, but you have an embedded point at the node. And this, at the same time, degenerates to the reduced nodal plane curve and a point in P3. So you sort of see through this example that if we want a stack of all curves, it's natural, and we want it to be algebraic, it's natural to, allow, if you allow this curve with this embedded point, then you better allow deformations of it. So you have to allow non-connected and also non-pure dimensional one curves. All right, but that's not really, it's not going to cause us much problems. Okay, the second issue, we also need to redefine what we mean by a family of curves. And so a family of curves now is a flat, proper, and finally presented morphism where this C may be an algebraic space. And then we have a family also of n-pointed curves. And it's just a family of curves as is just defined with n arbitrary sections. These are completely arbitrary. They could land in the singular locus. And the reason now we want to allow algebraic spaces is because we want to get, as Alessio perhaps was suggesting, we want to get a stack. So we need our families to satisfy effective descent. And there's examples where it fails if you just consider families of curves where the total family C is a scheme. So we have these, on the right-hand side, we have this example of Fogishu, where there exists a family of genus 0 nodal curves, where this S is a smooth projective surface, and this is a smooth three-dimensional algebraic space. And the point is that it's not a scheme. It's based on Hironaka's example of a proper but not projective smooth threefold. And in this case, even the generic fiber is even a P1. So it's a generically smooth family of genus 0 nodal curves. Seems rather innocent, but if you want to, but this example indicates that we need to require the total family to be an algebraic space. And similarly, in the smooth case, there's even a family of smooth genus 1 curves due to Renault, where I think this is a normal surface. And again, this is not a scheme. So even if you want to define the stack M1, you're sort of forced in your definition of family of curves to allow algebraic spaces. But maybe I should point out that if you have a family of curves, if you have a stable family, then the relative canonical is ample, right? And that implies that C is projective over S, and in particular also a scheme. And so in these examples above, these families are not projective. But in the stable case, it's particularly nice because you could use the relative canonical to polarize your family, and so it is projective. And so to deal with the first thing we want in order to address sort of these arbitrary families, we need to prove that everything is tau locally projective.
Jarod, where Fulgesu's example, where is that? I hadn't heard that.
Oh, it's in a paper of his in 2009. I think maybe based on discussions with Edidin or not. Yeah.
Thanks.
Yeah. So here's the proposition we need to show. We need to show that if C to S is a stable family, sorry, is a family of stable, a family of curves, arbitrary family of curves, then there exists an tau cover such that the base change is projective over S prime. All right, and I'm going to outline a few techniques. I'm going to give you a couple sketches for how to do this. This proposition also takes some work. And it's sort of one of these things that it really depends. Yeah, there's multiple approaches to take, and it really depends what you want to use. And there's sort of a balance of sort of explicit, but maybe more clever arguments with more conceptual ones. So I'm going to give two flavors of arguments here. The first is going to be a very abstract, like local to global argument, where I'm going to throw a ton of machinery at it, probably way too much. And the second argument will be like a little more geometric. So we're trying to show, again, the proposition's written up here. The family of arbitrary curves, I want to find a tau cover so that it becomes projective. The first approach is going to be this local to global argument, where I'm going to sort of start with it, sort of the same sort of picture that we had last time, where sort of, I have my fiber here, and then I take the nilpotent thickenings of this point, and then I also sort of have the completion and the base change of the family to the completion. So all of these squares here are Cartesian. And so the first case is working with the central fiber. So just C0. And here, what you use is that something I haven't established, but you need to show but it's true, is that separated one-dimensional algebraic spaces are schemes. And moreover, proper one-dimensional schemes are projective. And what that gives us is a line bundle L0 on C0, which is ample. And the goal in both of the approaches is to extend an ample line bundle on the central fiber to an ample line bundle, at least in the tau neighborhood. And in the next step, so we need to get, in the next step, we're going to use deformation theory. Infinitesimal deformation theory says that that there's an obstruction to deforming like a line bundle Ln on Cn to a line bundle Ln plus 1 on Cn plus 1, and that the obstructions live in a cohomology group, which is H2 of the central fiber of the structure sheaf. And the point is that because we're dealing with curves, this cohomology group vanishes, therefore all obstructions vanish, and therefore there exists like line bundles Ln on Cn. So we get a compatible family of line bundles L1, L2, so on. And moreover, yeah, they're ample, and these line bundles Ln are ample because of the fact that ampleness is an open condition in families. We'll use this sort of repeatedly. So it's enough, once you know that the central fiber is ample, it's really enough just to extend the line bundle, and then you know you're going to get ampleness, at least in some open neighborhood. And now, one of the trickiest steps is to go from these nilpotent thickenings to information about the completion. And here we rely on a powerful result of Grothendieck called the existence theorem, which holds, here in this case, we have C hat, which is over a complete local Noetherian ring. So let's assume this is, to handle this case, we need to reduce to this case later. Let's assume that this is complete, local, and Noetherian. And in this context, if you have a proper morphism over a complete local Noetherian ring, Grothendieck's existence theorem says that there's an identification of coherent sheaves on the total family of C, I guess that's C hat, to compatible families. So what that gives us is, oh, first let me say a few words about this. I think you're probably asking yourself, we don't know that C hat is a scheme, right? And yeah, we don't. So in order to apply this approach, this definitely isn't the simplest method to show this. You need to generalize this growth index existence theorem to proper algebraic spaces over a complete local Noetherian ring. And to do this, you actually sort of follow the argument. If you remember how you show growth index existence theorem, which you probably don't, but if you do, the way you show it is you first show it in the projective case, because then you could use, you can surject on to by copies, by direct sums of O1 and so forth. And then you reduce to the projective case by using Chow's lemma. And so you first need to first show sort of a Chow's lemma that there exists a projective birational map to C hat over S, where this is now projective. And then you use Debye-Sage in a similar way to how you showed growth index existence theorem for the proper case. But anyway, yeah, if we're given this, let's take this as a black box. What it gives us is a line bundle L hat that maps to this compatible family of line bundles Ln that we constructed. And again, it's necessarily ample. Right, and now in the fourth case, let's assume now S is finite type over Z. And so in this case, you can apply Artin approximation. You'd need some sort of finiteness assumption like this to apply Artin approximation. And you apply it to the functor over S, which assigns, you could just take the Picard functor, right? And what that will give you then, that is this gives you in a town neighborhood of S in this picture, and a line bundle L prime on it, which is going to be ample in an open neighborhood of some point S prime over it. And then the final step is just to reduce to this case, to reduce to when S is finite type over Z, and here you use Noetherian approximation. So I don't expect you to follow all the details here, but maybe, yeah, if you can understand the general idea of this argument, I think it's a powerful method in moduli theory. Okay, let me quickly give you another sketch that's a little more geometric and certainly requires less foundations than this argument. And so the idea here is, again, we're sort of in a situation where we have an ample line bundle on the central fiber, and we want to sort of extend it to a line bundle on C. And you could imagine many ways you could do this, like you could try to use reductions on this to first assume that this total family is a scheme, and then assume that it's a reduced scheme, so that you know that it's like at least, and then try to look at the smooth locus inside that and extend it as a Cartier divisor and whatnot. And so there's many approaches you could take here. I'll follow one. I'll give you one approach that assumes that all the fibers are generically reduced. So this also implies that all fibers are generically smooth. And what that assumption tells you is that if you look at C0 here, if you look at that, there's a non-empty open locus C0, which is smooth and surjects over S. And so now what we do is we just, so CS may be disconnected. So we can choose points P1 to Pn in CS such that every irreducible dimension 1 component contains at least one point Pi. And we could take then L0 to be sort of, the line bundle, which is just the ample line bundle, which is just is given by these points. And then we want to extend these points to a section, but we use the Ital local structure theorem of smooth morphisms. And what that tells us is that there is in a town neighborhood. Maybe I'll just draw it in a diagram here. I have S prime Ital over this, such that when I base change this locus, that I have sections sigma I extending these points Pi. All right, and then once you're in that situation, you can just take the line bundle on the total family defined by these sections, since they land in the smooth locus. You get a line bundle, and then it's ample in an open neighborhood of S. Anyway, they're both sketches for what it's worth. All right. Any questions? All right, now we get to the fun part of the argument. All right, so we want to prove algebricity of the stack of all curves. All right, here's our pre-stack. I'm calling it MG and all. Objects are just families of curves with arbitrary sections. And morphisms are Cartesian diagrams that are compatible with the sections. Right, this defines a pre-stack. And the first thing we need to know is that it's a stack. And let's just handle the case when n is 0, just to simplify the notation. But in fact, to show this is actually easier than when we were trying to show that MG is a stack before, because we had to worry about effective descent for projective morphisms. Here, we can just descend it as an algebraic space, and so we get that it's a stack for free because we're allowing the total family to be an algebraic space. Precisely what we need to spell out is, so if we have a C prime over S prime, and let's suppose that we know we have this sort of situation where, and we're given an isomorphism, say between P1 pullback of this curve C prime to P2 pullback. And what we want to construct is a family C over S, right? And the way we're going to do that is let's just take the pullback P1 pullback C prime. So the fiber product under the first projection. Let's call this R. Suggestively is this a scheme of relations. So I have one morphism, which is just the first projection, but I could also compose with alpha this isomorphism and then take the second projection. So in fact, I get an Ital equivalence relation where the cocycle condition is giving me sort of the groupoid structure of this relation. And then I just take the algebraic space quotient. and this is my family of curves. And this is, yeah, so this completes that argument that it's a stack. Right. All right, moving on. So we want to show that the diagonal is representable. This might surprise you because we didn't even impose this condition in the definition of an algebraic stack, but it's really helpful to show first, because what this tells us is that this implies that any map to this stack from a scheme is representable. So in the end, what we want to construct is a smooth representable cover of our stack. And to get that our cover is representable, we're going to just show that the diagonal is representable. Again, I'm going to give this proof just with no marked points to keep the notation simpler. And what we need to show is that we have this diagonal. And let's take a scheme T mapping to it. Oh, and we take the fiber product, which is an ISON scheme. And here, this map here corresponds to two families. Let's call it C1 over T and C2 over T. And then this is the functor representing isomorphisms of these families. So it's a functor where, yeah, to a scheme S over T, you look at the isomorphisms from the pullbacks from C1 to, yeah, and from C2. And what we need to show is that this is an algebraic space. And so the first step is we're going to reduce to where C1 and C2 are projective. Right, because we know there exists an Étale cover such that, okay. Oh, I switched my base. Let's call it T. T prime to T, such that the base change C1 T and C2 T are projective over T. And then suppose that we know it in this case, suppose that we know that isom T prime of these base changes, suppose we know that this is an algebraic space over T prime, but yet we have a Cartesian diagram like this. But T prime to T is Étale and surjective, and T prime to T are also schemes. So this map is Étale, surjective, and representable. So once you know that this one is a scheme, it implies that this is a scheme. Oh, sorry, is an algebraic space. So it suffices to handle the case where both C1 and C2 are projective. And we're doing that in order to be able to use the Hilbert scheme. You could also try to show that the Hilbert functor, just for in a more general setting, just proper morphisms of schemes or even proper morphisms of algebraic spaces is representable. But here we're going to rely on the Hilbert scheme for projective morphisms. Okay, so here we are. We're still trying to show representability of the diagonal. We have two families of curves. Now we can assume that they're projective, and we need to show that isom is an algebraic space. And we consider sort of these inclusions of functors. we have isom, classifying isomorphisms, and then you also have the functor just parameterizing morphisms. And then we want to embed that into this Hilbert scheme here. And maybe I should explain how this works. That if I have, suppose I have an arbitrary morphism from C1 to C2, what I associate is the graph. So I take C1, embed it into C1 cross C2. And you can extend this. So this is just defining it on T points. It's similarly defined on S value points. So you have an inclusion of functors. And this, yeah, the point is that this we know is projective. And so it suffices to show that these inclusions are representable by open immersions. And we're going to use the following fact, is that if given, suppose you have a morphism family of schemes, diagram of schemes, suppose both of these are proper, then the claim is that the locus where the morphism X to Y is an isomorphism is open in T. In fact, there exists an open subscheme such that, in fact, whenever you have a morphism S to T, then XS to YS is an isomorphism if and only if ST factors through T naught. And so this fact, this fact implies that this map is a representable open immersion. So we only need to look at this inclusion. We need to show that this inclusion is also representable open immersion. And here you just note that a subscheme Z inside C1 cross T. So a subscheme, like a point in this Hilbert scheme that is a subscheme, is the image of a morphism if and only if, well, you just consider this composition under the first projection, as long as this is an isomorphism. Right? Because then Z is going to be identified with the graph. And so again, yeah, so we use the fact again, implies that it's a representable open immersion. And so this completes the proof that the diagonal is representable. I'll stop for questions.
I'm assuming the diagonal will usually not be representable by schemes.
I guess we didn't show that. We just showed that the diagonal is representable by algebraic spaces.
Do you know if it will be representable by schemes or not?
I doubt it. Yeah, I really doubt it in this case.
Okay, that's fair. Thanks.
Is this Hilbert functor an algebraic space or a scheme?
Oh, this Hilbert functor is a projective scheme. And this is where, this is why we're reduced to the case where C1 and C2 are projective over T. We're using sort of the fact that the Hilbert functors for arbitrary projective morphisms are not only representable, but they're representable and they're projective. We don't need that projectivity here. We just need that. We just need that this is, the more important point is that this is a scheme or even an algebraic space.
Okay. So in this special case where C1 and C2 are projective over T, then actually this pullback is a scheme, since it's like an open immersion into this Hilbert scheme. Am I understanding?
Exactly. Yeah. In this case, yeah.
Okay.
In this case, it is. But if you look back here, yeah. If you look back at our argument in general, so yeah, in the end, we showed that this was a scheme. But in general, you may have families that are not projective, so we don't really have any control over this. The best that we can show is that it's a algebraic space.
Okay, cool. Thanks.
Yeah, it's a good question. All right. Okay. So now let's get to
So in that case, is that map from a scheme the Attell presentation of that algebraic space?
Yeah, exactly. Yeah, exactly. Yeah. In this diagram here, which we're trying to show that this is an algebraic space, and we found an Attell representable cover where this is even a scheme. And so this gives you, this is an Attell presentation. And this map is Attell surjective and representable because it's the base change of just a Attell surjection of schemes. And so we proved that this is an algebraic space by constructing the Attell presentation.
So is this isomorphism functor always a scheme between two projective schemes?
I think so. But yeah, I think this I think the argument I sketched here shows that this isom is always going to be a scheme because it's a subfunctor, open subfunctor of the Hilbert scheme, which we always know is a scheme.
Okay.
And projective.
So going back to one question a few lectures ago, then the automorphism group of a projective scheme is always a scheme because the functor of points should be this isom functor, right? Between itself.
Yeah, I think that's right. Yeah, I think that's right. Yeah.
Okay, thanks.
The automorphism functor is always a scheme. Yes. Yes. Yeah. Okay, so we know that the diagonal is representable. Now the last thing we need to show is we need to construct a smooth presentation. And so we're trying to we're trying to show that this theorem, that MG, the stack of all curves, is an algebraic stack and locally a finite type over the integers. And so I'm going to make a couple of reductions here. But we're only going to do it. Oh yeah, we're going to do it when n is 0. But this is enough because if you add one more marked point, then this is the universal family. And so once you know that this is algebraic, you also get that this is algebraic. Right, and now what we really need to show is that for every projective curve C0, we need to find a smooth representable morphism to the stack that has C0 in the image. And so the way we're going to start is let's choose an embedding C0 into some large projective space, and let's arrange that H1 of O of 1 is 0, right? That we can do by Serre's vanishing, perhaps by taking even a further embedding under like a Veronese. Okay, and let's let P of T be the Hilbert polynomial. And we're going to consider the Hilbert scheme. We're going to take H to be the Hilbert scheme of this projective space over Z with Hilbert polynomial P. And so we know, the point is that we know this is projective over the integers. In particular, we know it's a scheme. And we have a universal family. We have a family of curves C over H that embeds into projective space over H. Right, and we even know there's a point inside H whose fiber is our curve of interest, C0. So this is isomorphic to the fiber, yeah. And we have a morphism from, oh, before I get there, let's see. We can apply cohomology and base change. Implies that there exists an open subset H prime inside H, open neighborhood of our point H naught, such that for all points in H prime, H1 of the fiber S of O of 1 is 0. All right, so yeah, we're gonna, it's sort of critical to use, we'll use this vanishing of H1, and we need to know that it vanishes for all deformations too. And we have a map from H prime to the stack of all curves that takes, a curve embedded in Pn and just forgets its embedding. And we even know, since H prime is a scheme, we even know that this map is representable. So what we need to show is that it's smooth. And we're going to use, to do this, we're going to use the formal lifting criterion. In fact, I've spelled it out on the next page. So let me just go here. So we need to use the formal lifting criterion, which states the following. Okay, so we consider commutative diagrams like this, where A to A naught is a surjection of local Artinian algebras with residue field K, and we're even assuming it's a small extension, well, because we can. And so I'm in the setting that, okay, so I have a point over the residue field that's just embedding C inside Pn. And what we're interested in is knowing if there's a dotted arrow like this. So this translates to this question, if you look on the right-hand side, to the following, that we have over the central fiber, if you look in the center, that was the eraser. If you look in the central fiber, we have C embedded in Pn, and then we have some deformation of that to this Artin ring A naught, and we also have an embedding of C naught into Pn, and then we have a deformation C, but we want to know whether we can extend the deformation of C to an embedding inside to Pn. And the way we're going to argue is we're going to make a simplifying assumption here, just because it makes the deformation theory easier. A similar argument works in general, but here we're going to assume that C is a local complete intersection, and we're going to use deformation theory. Where extensions, if I take C0 over spec A0, and I'm looking at extensions to a family C over this, so this is flat and this is a pullback, these are classified by deformation theory, which we're relying on here, by X1 over omega C OC. And on the other hand, extensions like this maybe I should put that in color. Yeah, extensions. Like this are classified by a different cohomology group. They're classified by just homomorphisms from I mod I squared into the structure sheaf, where I is the ideal sheaf defining C inside Pn. And right, if you want to think, this is just the global sections of the normal bundle. But now so now we can wrap this up, because this simplifying assumption tells us that, because it's a complete intersection, that the curve inside Pn is locally cut out by a regular sequence. And it even tells us that if you look at the conormal bundle I mod I squared, it's locally free and it sits inside an exact sequence. If I take the differentials on Pn and restrict to C, I have this exact sequence. And applying homomorphisms into OC gives me a long exact sequence, of which the relevant part for us is the following. I tip hom I mod I squared into OC, and then I get an x1 omega C OC, and then this maps to an x1 omega C restricted to Pn, and an O of C. Okay. Yeah, you can't see. O of C. But this here is a vector bundle. Sorry, I've written it wrong. That's confusing. It's omega on Pn restricted to C. Omega on Pn, of course, is a vector bundle. So this is a vector bundle on C. So this is identified with H1 of on C of the tangent bundle of Pn restricted to C. And the point is we've arranged right. So we have the short exact sequence, and note that that this differential in the long exact sequence is what it does in terms of this identification with deformations is that it takes an embedded deformation. This takes an embedded deformation C0 to C. And note that we're given this deformation, and so it suffices to show that its image in this cohomology group is 0. And to that end, we use the Euler sequence restricted to C, tells us that the structure sheaf maps to O1 direct sum n plus 1, maps to the tangent bundle. And this has a vanishing H2. This has a vanishing H1. Because we've arranged it to be 0, we've restricted to the locus. Yeah, such that H1 was 0. And what that implies is that H1 here is 0. Because and therefore the cohomology group on the right-hand side is all 0. And so our deformation C maps to 0, therefore there exists this embedded deformation, which gives us the dotted arrow up here, and therefore this dotted arrow verifying the formal lifting criterion and the smoothness of our presentation. Okay, that was really a mouthful, but in the end, what we've shown was, just to recap, we've shown that the stack of all curves is an algebraic stack locally of finite type over Z. And what that means for us is that in this set of inclusions, we know that this final guy here, MGN, is algebraic. So and all of these inclusions are going to be open immersions. So this inclusion here, last time, we showed this is an open immersion. And maybe I'll just say in words, we showed it was an open, that the nodal locus was open in families of curves where the total family was a scheme, but you can use a tau descent to reduce to that case. So it works in this more general setting as well. And so, yeah, this is open. This is also open because, the locus, this is the open locus where the n sections are disjoint and smooth. Those are open conditions. And then this is the open locus. Well, one way to say that's open is it's the open locus where omega c is Neff, and Neffness is an open condition in flat families. And then this is just the stable locus, which we've shown is open. And this is the smooth locus, so this is open. And so we have this nice diagram. And the other thing, just to put some things in context, to like the first thing I showed today with the contraction morphism, is that interestingly, the contraction morphism, because it works in families, it gives us a map from MGN pre back down to MGN bar, which is a section. So in other words, yeah, the contraction map has a section which is an open immersion, and because it's not a closed, because this is highly non-separated, it's not a closed immersion. Right. So yeah, that's where we are. We'll continue next time. I'll stop the recording and then I can take a few questions.